All right. Hi, everyone. I'm Gautami. And okay, like today we are going to talk about multimodal models. So before we get started, do you see anything interesting about this slide? Anyone wants to take a guess? Yes. Yeah. But do you see anything interesting about the generated image? Is that Yeah, it is. So I tried to create a McKeldin library with the recent Meta AI's generative model, Imagine. It came out pretty well. Like I think it got like most of the details pretty good. Yeah, so that's what we are going to talk about today. Okay, so
You can talk about like how is that, but we can talk about.
yeah, we'll get to it. Okay, I mean, like when I share the slides, probably I'll give the prompt I used to create this. Um, what is multimodal learning? So before we kind of get to understand what multimodal learning is, let's try to understand what do I mean by mode. As humans, like we are kind of getting sensory information in like a lot of different forms. For example, vision is a sensory information, and then we have audio, and then we have touch and bunch of things. In our digital world, we try to capture all these signals in the form of like various forms, such as images, text, audio, video, and so on. Unfortunately, we are still like far behind on like few senses like touch and smells and so on. Yeah, now that we understand, essentially the field of multimodal learning is all about like can we combine like one or more of these sensory information or digital information and try to understand the world a little bit better. Can you guys think of like a multimodal system or an example for multimodal system? Any guesses? Yeah, that's great. Okay, I was hoping some of you will say like GPT-4, but I was going for humans. We ourselves are the perfect multimodal systems. Okay, maybe not perfect, like at least according to us, we are perfect. Like a lot of higher life forms, like mammals, are able to capture a lot of modalities and try to make sense of the world a lot better. Okay, next, let's try to understand why is it important. These days, like all you hear about are LLMs, and it seems like the text is ruling the world. However, that's only one part of the equation. And in fact, when we are interacting with the world every day, like even internet, in fact, like for example, the web content, most of it is multimodal. In fact, like a lot of data which is generated out there is video data, not text data, in fact. So it becomes increasingly important like to understand like these higher modalities like video, which is actually much richer than just text because it has both visual information as well as the audio information. And similarly, the field of robotics, like which is up and coming, like that's all you hear about these days, like everybody's introducing humanoid robots. So you see these great engineering feats like of robots doing parkour and interesting things. But however, they are so what do you say, like ignorant about a general, even the smallest things, like for example, trying to understand or predict the next action, like we are still so far behind because our multimodal systems are not so advanced yet. Okay, yeah, don't worry about too many details. I just wanted to show like a layout of like what a typical multimodal system model look like in this deep learning era. We take in like text, image, audio, video, and a bunch of modalities. And we try to combine them via like some sort of black box system in the middle. And we also want the system to be able to generate all these modalities. If you have used like GPT-4 as of now, it is actually able to accept like text and image modality so far, and it is also able to produce like text and image modality. However, it's still far behind, and it's not capable of doing audio and video, and so on. So yeah, like it's easy to, I mean, like for us, like I said, for us humans, like this comes extremely easily. But however, like AI systems are still so far behind. Okay, so these are some of the famous big names of multimodal systems. I mean, even though most of these are just bimodal systems, like anything more than one modality, like we kind of put them in the bucket of multimodal systems and deep learning. So for example, if you take Stable Diffusion, it accepts text and tries to generate images. And like I mentioned, GPT-4 accepts and understands images, and it's able to generate both text and images. And I'm not sure if you guys heard of this company, Suno. They're kind of text conditioned audio generation. And lastly, we have Gemini, which is as advanced as GPT-4. I think it's even more advanced. Like I think it accepts like audio and video files as well at this point. Okay, yeah, like multimodal systems include like other modalities like audio and so on. However, like in the interest of time, I will mostly talk about like text plus vision systems today. So like the how you combine these modalities also like can vary a lot, and I tried to bucket them in like a few boxes. So for example, like in the first case, like we want to understand, can we how you just merge these two information and do like some sort of a discriminative task, like for example classification or retrieval. And second, we talk about like text to image or video generation systems, like for example Stable Diffusion. And in the third part, like I'll talk about like how systems like GPT-4, which can accept like image or video and try to make sense of it. And lastly, there are a few models like which are trying to do any to any generation. They're not so good yet, but let's briefly touch upon it. So before we get started, like I want to discuss, like since it's an introductory class, like you guys need to understand like a few basic things before we can jump on to like a little bit more advanced topics. So yeah, probably like this is the most important slide in this lecture. The representation learning is like a foundational concept across like deep learning. Everything we do in deep learning is a form of representation learning. For example, in this very simple example, let's say like we have an image of a dog. Typically, we represent these images in the form of like, I mean, let's say like the resolution is like 128 by 128. And we represent this dog like as a huge array of just floating point numbers, like in your computer. It's just like 3 times 128 by 128, which is around like 50,000 floating point numbers. That's how much information is there in this image. However, like what people found is like you don't need all these 50,000 floating point numbers to represent this image. You can get away with like compressing it to like into a smaller representation. So this is that's what we did here. Like we took the dog, we kind of passed it over like some deep learning system, like which is nothing but a series of linear layers and non-linear layers, and we ended up with like a simpler representation like this 1/16. So yeah, like that's all more or less representation learning is. And like I said, so now that we have this representation, we can use it to do something. Like what that something is, like all the applications we have. Like for example, we can just use this representation to classify whether this image is a dog or not. Or we can just use this representation to create another image of a dog. Or we can just use this or just pass this information and try to reconstruct the same dog. So yeah, again, like, so representation learning is everything in deep learning. Okay, so and another important concept is autoencoder. Again, like this is also like a very old topic. And all we are trying to do is like how to build a representation for this dog. Like, for example, like think of it as this two different neural networks. The first one is trying to kind of compress the representation of the dog into like this smaller dimension of representation, and then we are kind of trying to build it back like into the original image of the dog. And as you can see, I tried to show like this and this are not exactly the same because it's very hard to build the exact perfect representation back. Again, like this is just like what we are trying to do is this looks like a generative model, but essentially what we are trying to do is like massaging one representation to another space and then trying to build it back. Okay, so transformer is just an architecture which is again, in fact, like trying to do a representation learning. All we are doing here is kind of pass, so it has like essentially encoder and decoder modules. So think of them as like two different black boxes. Like the encoder is just trying to convert like input text or images into like some high dimensional space, and in decoder is just another black box which takes this high dimensional representation and do something with it. Uh, okay, and again, like I just want, I mean, like, don't worry if you don't understand or capture many of these details. I'm just trying to introduce like some of these basic deep learning architectures, uh, uh, which we'll probably talk about a little bit later in the slides. And this is some, again, architecture called UNet. Here, all we are trying to do is like we start with an image at the beginning and try to compress it into smaller and smaller representations. And again, like we're kind of trying to build it back. So this kind of probably will remind you of like the autoencoder slide we have seen before, except like we kind of pass some information from this end to this end also. Like, but anyway, like these are all complicated architect. Sorry. Okay, so a JPEG image is represented in RGB space. So yeah, like each, like I said, yeah, good. All right, so these are a few primer slides I wanted to talk about. Like, if you have any questions, like we can revisit them. Okay, now that brings us to like the first part of the lecture. These are first like text and plus vision models. So yeah, these are like some of the famous architectures which fall into this category: CLEP, Alliance, GLEP, whatever. I mean, like CLEP is one of very famous models. Like I would even call it a landmark model because it's in fact came out like a couple of years back, and it has around like 15,000 citations already. And I think it's in fact like Google Scholar is not showing the correct number of citations. I'm pretty sure it's double this number. And for those of you who don't know, like accumulating like this number of citations in like a couple of years is like they're probably like less than 1 percentile of top papers. And why I said this is a landmark model is earlier, before CLIP, everybody, there are like many problems. Like, for example, if I want to classify cat versus dog, or maybe like just build a classifier for different types of cats, people are building like separate models for all of these tasks. What CLIP did is they built this unified model which can solve most of these tasks zero shot as in like which does not require like additional training. And how they did it is they kind of trained on like a lots and lots and lots of data. That's all they did. They trained on like around 400 plus image text pairs. And at the time, it's sort of unheard of, like nobody has trained like at that scale. And it kind of blew like all these pre-trained models like out of the water. At that time, it was kind of beating most of the leaderboards and so on. And this is kind of an architecture of the CLIP. Like I said, don't worry too much about details. The most important thing to understand is, so we kind of take images here and kind of use like an encoder model to just represent them in like some high dimensional space. And similarly, we take the text, which is like perhaps the caption for it, and kind of pass it through like a separate text encoder and kind of represent it in high dimensional space. And all we are doing is, in this particular high dimensional space, just try to bring these two representations closer to each other. And then if you have some other some other text, let's say like a cat, a Siamese cat or something like that, and keep that representation away from the dog image while bringing closer this Pepper the Aussie pup closer to it. So that's all they did. Like they're trying to do is like if image and text are kind of related to each other, their representations in the latent space should be closer to each other. If not, like keep them away from each other. That's all they did. And here are a few of the tasks like Clip is capable of performing really well. Like I said, so some of these are so this data set, Food 101 or even ImageNet or people were kind of training like separate models to solve these tasks because they are so out of distribution for earlier models that regular models underperform on these a little bit atypical looking images. Like for example, this is slightly harder image to guess, like this is a guacamole. I don't even know what's on top of it, but so yeah, like Clip was able to like kind of predict it really well. And similarly, like in this image, which is a painting of a husky, I guess, like however, the earlier models like were not able to recognize it's a dog, even though it's very easy for us humans to recognize it. And Clip was able to do really well on this data set. So these are like just a couple of examples. And so Clip is not a generative model. So Clip cannot predict what this image, so Clip cannot write in text for you what this image is. However, if you get this image and give it a bunch of options, it is really good at picking the right answer. So that's what Clip is able to do. That's why you can use like Clip for image to text retrieval task, or people have also used it to do like other way around, where given a text, you can try and given a text and a bunch of images, like you can use it to just retrieve the most relevant images for this. So in this case, like this person is searching for like fig fruits without flowers, and we have like a bunch of images. And all we did is like again like kind of compress this text into a representation and compress all these images into image representation and try to find which image is closest in space like to this text representation. That's all they did. And as you can see, like without any extra training, like you can use the Clip model, like for example, in e-commerce or places like that. Okay, and that brings us to the second part, text to vision generative models. And I'm pretty sure all of you have heard of DALI, Stable Diffusion, and Meta Imagine, Midjourney, Sora, and things like that. These are all different like generative models which came out of different companies, and most of them like more or less share like similar architectures or kind of training paradigms. In fact, like most of them share similar data as well. It is the open ones. Okay, so okay, let's start with looking at some fun pictures. This is one of the images generated by like Stability, like with one of the recent models. What they're trying to do is a painting of an astronaut riding a pig, wearing a tutu, holding a pink umbrella on the ground. Next to a pig is a robin bird wearing a top hat. And in the corner are the words Stable Diffusion. And if you tried this like 2 years back, the best figure you could get will have just pig, nothing else, or astronaut. And they won't even look realistic or even acceptable to even as illustrations. So and I mean the most impressive thing is like the level of details which are in the prompt and how much the model is able to like actually capture all of them. As you can see, like on especially this image, like it more or less captured all the details. Um, and similarly, like if you go in this Reddit thread, like people were like kind of trying out the similar prompts with different models. Sorry, this Twitter thread. And here I show like two examples like from other famous models, like that top one is with DALI, Lisa and DALI, and this one is with Midjourney. And so do any of you see any problems with these images? Any mistakes, problems? Yeah, yeah. So, yeah, like some of these models can't spell. That's one of the major challenges with some of these generative models. Yes. Yeah. So yeah, like spelling used to be like really hard, like few months back, and Stable Diffusion was sort of able to kind of address it in one of their recent models. I mean, I don't want to go into too many details about how they did it. I mean, what I'm trying to say is like these models are so well designed at this point, like that more or less they are kind of adhere to the extremely complex prompts and produce like really good generations, in my opinion. And a fun fact. The in the prompt has the word Robin, right? Like Robin is actually like the one of the creators of Stable Diffusion, and I'm guessing like that's an Easter egg in this prompt. All right. So okay, so how do these diffusion models work? I mean, without going into too many details, like diffusion models, you can think of them as some sort of denoising models. Like, think of it this way, like you have this black box system, which kind of begins with a noise, and each step, it kind of removes a little bit noise. And but after multiple steps, you end up with like a realistic looking image. That's all, like more or less it, what happens in I mean, in diffusion models. But how we are going to do it, that's like the slightly little bit more complicated part of it. There is like a nice math, like for example, we know how to go from image distribution to the noise distribution. And yeah, like there's like a lot of math involved, like don't worry about it right now. But what I'm trying to say is, like diffusion models, in fact, like this sort of processes have been around for like a very long time. Like in fact, like for some of these, the math behind it at least has been around for like 30-40 years. But what changed right now is the compute and the data. Like we have a lot of compute these days. Like people can't even imagine the amount of compute we have right now, like even like 15-20 years back. And the amount of data we have access to, that to good data we have access to right now is like unimaginable. So yeah, like the math has been there, but what changed the game is the compute and the data. And okay, like, let me try to give you like a little bit of mental picture, at least like of how diffusion models work. In this figure, like let's focus on the left side first. Like so, imagine we are training a diffusion model, and all in our data we have only cats and dogs. And what we do is we kind you can see like it's a bimodal distribution because we have only cats and dogs. And what we are doing is like we are mapping it from this bimodal distribution into like this unimodal Gaussian distribution. That's all we are doing. And inference time, we begin with this unimodal Gaussian distribution, and we randomly sample a point. And like I said, like we are just progressively denoising it until we reach one of the points in this bimodal distribution. And like I said, like we are just uh, turning one representation into another representation. Again, this is also a type of representation learning, and we are just using these complicated deep learning models to do the mapping for us. One issue with this model right now is, imagine like we want to create an image of a cat. And the thing is, like, let's say like, we started somewhere. We don't know whether that point will end up in a cat or a dog mode. And you have to keep sampling it until you accidentally come across a cat. And imagine like for you want to create an image of a black cat or something like that. Now that makes it even more complicated. You have to keep sampling it until you accidentally come across a noise which can actually map to a black cat in the distribution. So yeah, like it's kind of a, I mean, like let's think back to the prompt like we have seen before, like the astronaut like riding a pig, wearing a tutu. This is and imagine like there is very low probability you will in fact like accidentally get mapped to image like that. So That's where some of the innovations came. Again, like from one of the early papers were from OpenAI, and then we have the stable diffusion model. And again, this is like a very simplistic representation. So stable diffusion, two of the innovations introduced in stable diffusion paper is first they kind of condition this model on some sort of text representations. So all they did is they took a text transformer and they kind of give a text produce a text representation, and now what happens is like this text representation kind of guides the noise where to go. So if we go back to the previous slide, so what's happening is like instead you sample any random noise. However, your text embedding will literally be pushing it towards the kind of image you are looking to produce. Again, this is just a text assisted, like we are literally transforming noise into image while being guided by the text representation. So that's more or less it to it. Any question so far? Right. Okay. Now that we understand a little bit what diffusion models are, let's try to look at some of the capabilities. Like the first one is quite obvious. Like we begin with the text and try to generate an image. And the second thing is like image super resolution. So you kind of like start with like a simple looking image, like maybe 32 by 32 pixels, and you kind of can even turn it into like 1000 by 1000 pixels or something like that. And then we have like image editing and also like image condition generation and customization and so on. I'll show a few examples in a minute. Okay, so the first one is the image editing. So here, so far, like we have mostly looked at like images generated, given a prompt, let's say like you already have an image with you, and you just want to like kind of change like a few attributes in it. For example, in the first example, we have this Van Gogh's painting, and maybe we want to replace it with like roses. So that's what we did, like kind of give this image as an input as well as the text. And all we say is like swap sunflowers with roses. Or similarly, like here we want, in this figure, we wanted to replace like these fruits with the cake. Here we are kind of, we are kind of replacing objects in the image here, right? Like it's also possible to change the style of the image. Like, for example, here we have a short from short story. We are kind of trying to convert it into a realistic looking image, which is sort of very creepy. Okay, so this is one of the use cases. And we also have, again, image conditioned models. Like, for example, let's say like, I mean, like there is certain information which is hard to represent like purely in text. And like the bottom one is like a really good example of this. So you want to create an image for some reason, like of a man in a particular pose, like with hands this way. In this model, like so, what you do is you kind of input like the pose of the human, and if you don't condition with any text, like it kind of creates some images out of its biases. However, you can condition it on text also, like for example, chef or Lincoln statue. You can condition both on text and as well as this image or visual conditioning to create images like the way you want them to be. So essentially, like what we are trying to do with like this model and the previous model is we are kind of giving more control to the humans who are kind of trying to use these models. Okay, so I'll show like one fun video. Um, okay, so this is from this company called Kriya. And what they do is it's a real-time generation. You kind of begin with oops. Okay, let's look. So yeah, like the human is sort of playing around on the side, and the model is kind of generating it real time. And like for example, they're just adding dots and then kind of turning into flowers. And they picked up like a silhouette of a butterfly and kind of turning into a nice looking butterfly. Okay, so as you can see, imagine like you begin with this figure image, and you are kind of ending up in this image. So yeah, with tools like this, anybody who has some sort of a mental picture of how a certain image should look like, they can become like artists, or perhaps like without paying a lot of money, you can create some of these images yourself for simple use cases. So yeah, this is one of really good examples of showing I mean like a lot of people are sort of worried like okay fine humans AI is going to replace us humans but however the most likely use case is humans are going to I mean what do you say upskill using AI rather than like AI replacing them. It is not anytime soon. Okay. uh, do we want to see one more, or should we move on? Okay, somebody's interested. So let me see. Yeah. And so, again, another use case. Okay. Anyway, as you can see, this person just picked up like a bunch of pieces from internet, some clip arts, and just hacked them together and kind of ended up with like a really nice looking image. And if you know see carefully, there on the top, um, okay, there you can see like anthropomorphic yellow frog character wearing black suit, cute illustration. So as you can see, like they're kind of conditioning on text as well, along with the image input. This is sort of similar to like control net or the previous examples I have shown. I mean, like some of the interesting aspects are like, for example, early on in the video, as soon as you put the human here, as soon as you put the human here in this figure, it kind of started making hands yellow. Like, so yeah, diffusion models sort of have like a little bit of world knowledge. I mean, even though this is not like a feasible, I mean, it's not a good generation, the second, but kind of surprised me. When I looked at this video first time, immediately changed as soon as you put the human and the frog head together, immediately change the color of the hand. So yeah, these models are like super impressive. Okay, all right, those are all the examples I have for this. Okay, let's move on. Okay, the next set of capabilities are these personalization models. And they all started with this model, a technique called dream booth. I mean, like, imagine you have a dog and you want create paintings of your dog, like in different styles, or like you want to make like cute outfits on your dog to share with your friends or I don't know family. And what they did is they took a diffusion model which can accept like a few images uh, of an object, like in this case, this dog. And all they do is like the fine tune the diffusion model a little bit on these images, and turns out you can essentially embed these new characters into your model as well. And as you can see here, this dog now can be painted in Van Gogh style or Rembrandt and so on. So yeah, this is pretty cool. Here's another example of like somebody wanting to create like some Elsa in the style of paper cutout. Again, like they kind of fine tune the diffusion model on a few paper cutout style images and so on. So I mean, the difference between these two slides is like first in the slide we are kind of trying to inject this particular object into the model, and in this case we are kind of trying to inject style into the model. So yeah, turns out people have found like a lot of use cases for the dream booth, and it's pretty exciting. So I kind of tried out this paper cutout model uh, with with uh, with a terrapin. And in this one, I kind of tried out without any conditioning on the colors. And this one I kind of asked it to make them in red and yellow. I think it's pretty good. Okay, so again, this is sort of like a style transfer technique. This is another example here where someone has trained like diffusion model on Simpson style. And all of these are sort of generated images from that model. Unfortunately, I don't have the prompts like of how these images are generated. So I don't really know some of these characters. I'm guessing this is Harry Potter. I'm guessing this is Lara Croft. And I want to say this is Gandalf. I don't know. Okay, so yeah, and I just briefly want to touch upon what diffusion transformers are. So far, until a couple of years back, not until last year. So most of the diffusion models have a denoising unit as the black box, which kind of starts from a random noise and turns it into like a realistic looking image. However, like a couple of years back, there is this paper which kind of replaced like unit with transformer. That's all they did. And again, like a slightly simplistic representation because the actual architecture looks like slightly more complicated. Again, like all of these are sort of like engineering marvels rather than I would say properly grounded in theory or anything like that. Like most of the deep learning is like empirical science. Like we just don't know most of the time why anything works. Uh, probably the only winning solution all the time is like a lot of data and a lot of compute. And at the end of the day, any architecture would work. That's what we are realizing recently. There are a couple of reasons why diffusion transformer is going to be like the future of at least generative models, because particularly because one reason is the transformers are slightly easier to so when you're training on a lot of compute, what I mean by that is you train on a lot of GPUs which are connected on like spread across like nodes or and things like that. It's easier to kind of do like parallel training, model parallel training on diffusion on transformers compared to units. That's mostly the reason as far as I'm aware of. Okay, now that brings us to this. So you must have seen this tweet or Elon Musk going around asking who should be the president, transformers versus diffusion. Uh, I'll give you guys a chance. Like, can you now that you heard me speak for whatever, however long, can you tell me what's the problem with this tweet? Not politically, nothing to do. Like technically, there is something wrong with this tweet. Can you guess? Yeah, exactly. So it should have been transformers versus unit rather than transformers versus diffusion, because diffusion is just the way you train stuff, and transformers is an architecture. So yeah, it's just like transformers and units are architectures, while diffusion is a training paradigm. So yeah, next time if any of your friends code this, like correct them and feel superior to them a little bit. So far we have seen image diffusion models, and I'm sure all of you or most of you have heard about this model called Sora, which came out of OpenAI. very recently, like I think less than a couple of months back. And in fact, like this is one of the most impressive video generative models, in my opinion. And some of the generations are like literally blew my mind. And so let's look at like a few generations. Um, Yeah, so in this image, like sorry, in this video, you might have seen you can see, right, like it literally has a glass shell, and like there is literally grass and some life forms within living inside the shell. And I mean, I would say like the level of detail is amazing here. And let's look at summer videos. And this one is like one of my favorites. Yeah, I mean, like, I mean, some of these generations look so insane and so realistic. Yeah, so it's been like truly impressive. And however, can you guys tell me like what's wrong with this video? I mean, I'll give you a clue. Just more or less focus on the first few seconds. Sorry. Okay. Any guesses? Yeah. I mean, other than that, okay, fine. Yeah, that's definitely. Let's say like this is a fantasy scenario. Let's say like butterfly flies underwater. Definitely, that's a biggest problem. And okay, yeah, that's again like that's a good point. That's also another factor. Any other guesses? All right. Yeah. Mhm. The motion of the sky. Oh, okay. I didn't pay attention to it probably. Okay. So, I mean, anyway, the thing I was going for is the butterfly goes underwater and then it comes back up and its wings are still as they're dry. That was the biggest problem I had with it. I mean, you would expect it to be a little bit wet, but apparently it's not. Okay. So, that's, do we, okay, like, we can look at one more video. Okay, let's look at this video. All right. Anyway, okay, like Sora is like super impressive. However, there are like a lot of problems with it. And this is the little bit of information they revealed that they use like a diffusion model, video diffusion model on Transformer. They basically like that's all they did. They kind of took the video or a bunch of frames and then they kind of like used an encoder to kind of convert it into like some high dimensional representation, just flattened it and trained a diffusion transformer on it. Again, like there is no like great novelty in terms of architecture. All they did is they took up like a pre-existing architecture. Their novelty mostly lies in like amount of data and compute. Okay, like again, the just to show like the power of compute, they kind of in fact like give an example. Given like a fixed amount of data, and they kind of showed like three generations. So first one is base compute. We don't know how much it is, like probably like a million GPUs. And they just like made the compute like 4 times, and they made the compute 32 times. And you can see like the level of improvement, like I mean, it's just so crazy. Like so this was not even looking like a dog in like in this first video. And it became like really nice looking dog, like with a very realistic motions and so on. So like again, like so it all comes down to like data and compute, and transformers more or less work at this point for every modality. However, I wouldn't say like that's the end of the world. Like, of course, we need some innovations in terms of architectures also. So yeah, so far we have seen like a lot of impressive images and videos. And so does that mean like the image generation or video generation problems are solved? Unfortunately, it's not the case. Like most of the times, the generator images you look at on internet are heavily cherry picked. Like that means the human has tried like multiple times to just get like this good image, and that's what they share, right? Like usually. So here are a few of the failure cases from one of the stabilities models like SDXL. So as you can see, like they're trying to create like leaves growing out of the hand palm, and all they could get is like a put a leaf on top of the palm. And similarly here they're trying to do like a TV show with lions hugging a giraffe, and they literally couldn't get it because this is so unlikely that yeah, the model. I mean, the thing is like when you're training on like a lot of data, model has some biases, and it's hard for the model to in fact like generate some of these scenarios. They are extremely unlikely. Again, like there are some nice papers trying to attempt on like how to fix some of these cases. In fact, like they gave like really nice names to some of these failure cases like that. So in the first example, like they're trying to create like a pink sunflower and yellow flamingo. And we all know like flamingos are pink and sunflowers are yellow. And so what is the most likely scenario for the model is like just create like a pink flamingo and yellow sunflower, which is what it does most of the times. And so yeah, they kind of call it like a leakage in the prompt of semantics. And similarly, like here they're trying to create like a checkered ball in a cluttered room. However, the room also became checkered in like most of the cases. And sometimes like it kind of neglects parts of the prompt, like it doesn't even generate, like for example, horn lion and spotted monkey, like it just creates like a regular lion and monkey. So these are some of the failure cases, and there are like some band-aid solutions to this at this point. However, like it's a kind of an active research area. Again, another big issue is memorization. So these models, like when they're trained on like millions and millions of images, you would expect them to not memorize any of them. However, it turns out like some of the diffusion models like literally regurgitate the images from training data. For example, here, this is some video game poster called Bloodborne, and this is the generation, and this is the original image from which it is copying from. And because of that, like stable diffusion is kind of under a bunch of lawsuits and stuff like that. Okay, so this is my research. So if any of you are interested in it, like reach out to me. Again, like other than like exact copying, we also see like a varying level of style copying. Like in this case, the first image we look at like Starry Night by Van Gogh. As you can see, it's more or less copying both content as well as style. But as you keep moving to the right, like the model is kind of retaining the style of the artist, but not necessarily the exact same content. Like for example, this is Alfonso Mutra's paintings, and the model kind of retains the style, but it does not copy content anymore. Again, like a bunch of artists are kind of suing Stable Diffusion, saying, okay, you are copying my style and so on. However, I mean, like there are a bunch of issues with this. So first of all, there is like an ethical problem, which is you should not be training on copyrighted data without compensating them. And the second one is the scientific problem, where these models are not technically supposed to like memorize these things. So that's what I was mostly interested in, like and we kind of proposed a bunch of ways to make the model not remember stuff. Okay. So let's conclude this section by talking about a few of the open problems which are there. First of all, metrics is a huge problem in generative modeling right now. And everybody is so obsessed with LLMs, like that's all they do. They kind of keep introducing a benchmark every week. However, in diffusion models, benchmarking and metrics are a huge problem. So I mean, like when you build a model, you kind of create some of the images, and some of them look nice, some of them don't. But we cannot qualitatively conclude some model is good or something is better than the other. You need to have some sort of quantitative evaluation as well. And right now, the metrics we use, in computing, like how good the model is, they're not good at all. And this is a very important field and an active area of research. And the second thing is failure detection. So far, the failures I have shown are mostly like humans trying out things and kind of concluding, okay, fine, they're failing this sort of scenarios. However, it's not like a scalable thing. Like you need to detect failures automatically, and so that we will be able to fix them at scale. So this is another important area. And again, faster generation is another thing, because diffusion model is an iterative process. Like you have to do multiple steps to go from like noise to image, which is sort of slow. However, things are catching up in this aspect. We have like really fast generation and so on. And lastly, I would say better architectures is definitely an important problem, because right now everybody decided, okay, we will use transformer for everything. They gave up. It's quite possible, like there are even better architectures, which will kick like transformers to the curb, and probably one of you will be inventing those. And lastly, everything in video generative modeling is an area of research, because we barely scratch the surface there. And you would think like Sora is good, but Sora is not. It's good. It's definitely a great first step to inspire a generation of research, but it's still not good enough to be used in practice or in industry. Okay, so that kind of concludes the second section. Do we want to look at some demos? And, okay, you guys need to supply me with some prompts like here. Okay, so this one is okay. So this one is like a generic generative model. Okay, any suggestions for a prompt? Anyone want to give me a prompt? Testudo? Mascot. Probably it wouldn't know what testudo is, but I can try terrapin. Uh, uh, a painting of terrapin you want to do? Any colors, preferences? Okay. Okay, Maryland style. Let's try. Okay, in the meanwhile, let's try something else as well. So this is the style customization model I have shown before, the paper cutout style. Let's do um, University of Maryland here, maybe. I doubt it knows it, but let's try. Okay, generated. What do you guys think of it? I guess it didn't get the Maryland colors right. Sorry? Maryland flag style. Colors of my Maryland flag color. Okay. Oh, I'm surprised, because I definitely did not get this last class I tried. Okay, it got M right. Wow. Yeah. Maybe I'm not. Um, okay, I guess this model doesn't know so much about Maryland. Yeah, let's move on. I have some more stuff to cover. Okay, that concludes like text to vision part of the lecture, and the next part is, oh, we have all right, I'll quickly go over this. So essentially, we looked at like text to image, and the second part of the equation is like how do we go from vision to text? Like these models which can accept like visual information and kind of try to make sense of things. This is one of the examples from Gemini. And as you can see, they gave like an image of some vegetables and egg, and the person is asking like, okay, what should be the next step to make a veggie omelette, and the model is sort of able to predict and stuff. Um, okay, maybe I can move on. All right, so another one of the landmark models in vision LLMs is this model called Flamingo, which came out of DeepMind like few years back. Why I say landmark is this is one of the early models which showed it is possible to build like really powerful vision LLMs, which are capable of a lot of capabilities. So before this model, most of the vision LLMs are kind of like just used only for captioning tasks. However, in this model, they showed like first of all you can basically add skills to the model directly, like in the test time. In this case, if you're as you can see they're not asking the model any question. All they say is like, okay, they give it few examples. We have this chinchilla, and it is found in particular location, and this is Shiba is found in Japan. And what is this? And it was not only able to predict this images of a flamingo, and also predicted like where this is from. So this kind of one of the examples of like telling the model the kind of information you want from it and in the format you want it. And similarly, in this case, this is just a counting problem, right? Like instead of asking how many giraffes are there in this image, they're kind of telling the model, like literally teaching the model, what the format they want in, and also the kind of task they want the model to do. Okay, so that was Flamingo, and video. Just to give you an example of a video LLM, so Gemini 1.5 Pro is literally the only open source model which can accept like extremely long, sorry, not open source, closed source, which can accept very long videos. And in the paper, they kind of give an example of some video which is like 44 minutes long. Literally, there is no other model out there which can accept this long videos right now. And I'm interested. I mean, these examples are like so impressive that they're saying like, okay, what is the information on the paper which somebody pulled out of their pocket? And in fact, like in a 44-minute long video, first of all, it needs to localize to that exact point where somebody is pulling something out of a video. And on top of it, like it has to literally try to understand what is there in that particular frame as well. So this is very trivial for humans. However, like this is a very complicated task for most of these models. And this is actually a very fun example. So here, what they did is this is somebody drew a painting of an object which appeared in the video, and they said like, okay, what is the time code where it happens? And the model is basically like not able to like match this sketch to an image, and in fact it's able to give back like the time code. So these are some of the impressive capabilities. And like I said, even though I said like this is the only model, it's not because it's impossible to build it, but we are so early in this research that I'm pretty sure like by end of this year we'll have many impressive open source models with these capabilities as well. Okay, lastly, just want to touch upon all-to-all models more or less Gemini and GPT-4 are sort of they can accept and generate text and images so far. And we have like a few open source containers as well. However, they're not too good. like for example, unified IO. Again, it's very similar schema I have shown in the beginning. The model sort of acts like a bunch of these modalities and kind of tries to generate a bunch of these modalities as well. Let's look at few examples. Like this is a snapshot from this paper, Unified IO from LMAI. In the first image, bunch of image, an image of a bunch of food items is given, and they're asking like, okay, what can you make from it? And also, in this case, they're kind of asking the model to localize certain objects, or here they're kind of asking, like, given an image, like compute the depth and so on. Similarly, like these models also have like a model editing capabilities, like given this doc, it can view a caption, it can like kind of make it into sunset style or change the color of like certain objects in the image, like making the bridge red, or you can remove the bridge and so on. But anyway, like again, bunch of these are these are all cherry picked examples. Honestly, if you try the model, it's not very good. Again, like also like very we are in a very nascent stage in this field of research, and it's pretty exciting. Okay, I don't think I have time to do a Gemini demo. I briefly want to touch upon like web agents. So far we have talked about like a bunch of text to image, image to text, and so yeah, these are all nice to play around, but do we have any use cases for this? Why are these companies spending millions of dollars building these models? So one of the use cases is web agents. So in future, like a lot of people predict like we won't be interacting with interfaces to do a bunch of tasks for us. For example, sending an email or trying to find an object, shop an item, or I don't know, like maybe even plan your vacation. So that's what people are trying to do right now with these web agents. So I mean, it's a simple schematic from one of the papers. So or more or less, like you are kind of interacting with an agent, and the agent is kind of doing tasks for you, like where you kind of can give it like intermediate inputs, or maybe it can do the task end to end for you too. So this is very new. Like honestly, like there is literally only one big company like doing this. Maybe I can. I mean, I just wanted to show you a demo for this, not demo, sorry, an example of like how one of the use cases they have shown. Yeah, so here somebody is like trying to rent a, they want to rent a house, okay? And in fact, like in this video, there is an audio. The person is not even typing, but they're talking to the agent. And yeah, they're kind of giving information on like the budget and how big the house should be. And none of the interaction, like the agent is taking care of it, like the human is not interacting with the screen. Okay, I guess that's about it. All right. Anyway, this is just one of the examples they have shown. Like, just feel free to look at their website to see more use cases. Okay, so let's look at some of the open problems in this all-to-all sort of models. Like again, we need better architectures. One of the bigger problems is like, yeah, transformers work, but however, everybody is like just using the exact same tool for everything, which is kind of like stifling innovation a little bit, in my opinion. And again, like we need better ways to learn and how to fuse multimodal representations together. And we need efficient models. Like right now, most of these models you need like huge GPUs. However, I mean, like the future is going to be like smaller and smaller models. Like that's an important field of research. And again, lastly, like metrics is a very important field here too. Like we just don't know. We build these models and we kind of don't know how to measure how good they are, other than a vibe check, I guess. All right, so that sort of concludes my presentation. Like I shared a few of the useful links. These are sort of advanced materials. And thank you so much for attending the talk.